came from, in its simplest form, it came in classical thermodynamics, where it had the following form. Here. Restricted to closed systems, that means systems with fixed mass, homogeneous. The models used for 2R and WR made sure that the processes that were considered were reversible processes alone. However, soon it was realized that the first law is a more general principle and not restricted to reversible processes alone. And now to extend this to a fluid flowing, we have the restriction of a closed system or homogeneous system. Nor do we want to be constrained by restriction to reversible processes. We have to generalize this equation. So generalization starts. The first step is that the closed system corresponds to a system of fixed mass, and here it would apply to a body. A collection of material points of fixed mass. So the derivative here is a simple time derivative. The total internal energy will be now replaced by the substantial derivative. And we have the internal energy as well as the kinetic energy, because that was neglected in classical thermodynamics. Would have to be equated to the rate of heating. This is the rate at which heat is in to the body, input to the body. This is the rate of work done by the body. Rate, both of them refer to rate. So now we want to have kinetic energy is, so we take up each one of these quantities. Internal energy is the total internal energy of the body, but just as have the total mass of the body, but the density, mass density could vary from point to point. So to take such effects of the continuum into account, we will represent E as integral rho times epsilon times dV, where epsilon is clearly the specific internal energy, and here it is per mass. So internal energy per unit mass defined at every point in the system. The system is homogeneous. That means the specific internal energy doesn't change from point to point. Right? Then we would this can be taken out, but then in general we would have to keep it inside the integral. E is given by again half rho squared dV. So half mv squared, but here again the velocity as well as the density can change, and so we would have this the v squared is nothing but v dotted with v. That is the kinetic energy. Coming to the rate of heat input, just as the force could be transferred to a body, there are two kinds of forces we considered. One is the contact force, which requires specification of the stress tensor on the surface bounding the body, and then another is a body force, which requires specific force density, right, at each point within the body. So just like that, we would propose two forms of heat transfer. One is the heat that is transferred across the surface bounding the body, and so Q are being written as integral QdA plus integral OR dV. Two kinds of heat transfers are possible. This is often referred to, this is the heat flux, and this is a heat transferred regarded as the heat transferred through radiation. Radiation is regarded as the heat transferred in terms of a body source, right? Where R may be regarded as the rate of heat transferred per unit mass through radiation. It has to be specified every point within the body. Now the heat conduction, the exact analog to the stress vector is this heat flux scalar. Now it is. This is actually a function of not only the position and time, but also the outward norm which has been a body, and so this is heat transferred. The flux can depend on a point x on the surface at a time t, let's say, but it would also depend on the unit normal, right? Outward normal. Using similar arguments to what was done to prove the Cauchy's theorem, it is possible to show that this implies the existence of a heat flux vector whose dot product with the unit normal would give the heat flux scalar. So this is the exact analog of the Cauchy's stress theorem. Interestingly, it was proved by Stokes almost 30 years after Cauchy proved it in a more complicated case. But there, you have a stress vector which is dependent on the normal. You have to prove the existence of the stress tensor. This is easier to do because the heat flux is a scalar, and then we have to show that it is dependent on normal is actually determined. The dependence on the normal is given in terms of the dot product of the flux vector. Right? So this is really a function of x and t function. In this course, as has been done in most of the books, we are going to neglect the effect of radiation. So we will restrict ourselves to heat transfer due to conduction alone. You can ask, what about convection? We have normally taught that there are three forms of heat transfer: conduction, convection, and radiation. So no need in this generalized approach to consider the effect of convection separately. It will come automatically. We are after considering the effect of fluid flow. The heat transfer due to convection will come about automatically due to the fluid flow. No need to separately account for it in QR. In that sense, heat transfer to conduction is not as fundamental a mode of heat transport as conduction or radiation. You could say that. Not as distinct. It's sort of coupled with the fluid flow. Right? Now, what about work done by the body? The rate at which work is done, right, it depends on the forces. So it requires a mechanics, and of course first law can be generalized into various other forms of energy transfer other than through mechanical work. Here we consider what is mechanical work. We have mechanical work is performed by mechanical forces. We consider two types of forces, namely the body force and the contact force. We have to see how they contribute to work done on the body or by the body. Right? So work is often defined as F dotted with dx, where dx is a displacement vector. So clearly the rate of work done would be F dotted with dx by dt, which would be the force dotted with the velocity. Right? So that's the basic idea. Here we have to deal with force densities. So those force densities dotted with velocity have to be integrated over the whole volume. So we may obtain WR actually minus WR, because when we talk about the body force and the stress force, we are talking about force exerted on a particular body by the fluid outside the body. Right? So we are really talking about work done on the body. Right? So since here WR is defined as the work done by the body, minus WR would be work done on the body, and that is what was now equal rho V dotted with V dV plus integral T dotted with V A. The work transfer also has two kinds of sources, one coming out of the contact force, which is transmitted across the surface, and the other which is coming out of the body force. Right? So with this now, we we can put together the basic overall. Let's look now at the left-hand side. Left-hand side would be d by dt or into the rho epsilon dv plus integral half rho d square dv. So using a particular form of the Reynolds transport theorem, which refers to the substantial derivative of an integral, in which rho is one of the factors in the integrand, I can write this as integral rho actually d by d epsilon, let me write it first separately, plus integral half rho dv square by dv, which can now be written as integral rho d by dt. Volume integral. So the idea, first step, as I said, is to obtain the local energy balance, the local first law of thermodynamics, extended to include all these effects which were not considered in the classical thermodynamics of homogeneous bodies and reversible processes. Right? So now I want volume integral everywhere, and then whatever area integrals are there, I will convert them to volume integral by using the divergence theorem and get an equation which is the sum or difference of integrals, all of which are volume integrals. I will group all the terms together and then equate the integrand to zero to get the local equation. That's the procedure we follow throughout, both in the mass balance as well as in the momentum balance, as well as in the angular momentum balance. Right? So that is what we have. So this is the left-hand side. Let's now look at the right-hand side. So QR, so we are not considering the radiation effect. So this would be right-hand side would have integral 2 dotted with n dA. That is coming from the, which should be minus actually, because we have this 2r is the rate. Yeah, actually 2r actually must be minus, and so minus 2 dot n, because this would give the 2 dotted with n is actually going to give me the net heat transfer, rate of heat transfer out of the body. So I have to put a negative sign to account for the fact that there's a sign convention in the first law. All of you are aware of it. Depending on the sign convention, it will depend whether you are writing q minus w or q plus w or minus q minus w or minus q plus w. So when you take the rate QR as a net rate of heat into the body, then I can write the, and WR to be the net rate of work done by the body. Then I can write this QR minus WR. When I am writing it in terms of the heat flux, I would have to take that negative sign into account. So Q is really the flux representing the heat flux out of the body. And that's how I have to take it. So the right hand side have minus and minus W on the sphere. That would have to go V dotted with V dV plus D, which can now be written as n dotted with d dotted with d dA, because that's certainly needed to further reduce it to a volume integral, which is what I want. So there are two terms that I have to reduce to volume integral. This can be very easily shown to be minus the divergence of the efflux vector. Actually, what I have is I n I. If you look at the like OB dot m, right? So that became the divergence of OB. So that's very easy to see. Plus rho b dotted with b dv plus this I have to reduce. I haven't quite yet conquered this time because this now involves a velocity, dot product with velocity. So clearly, this is the vector, this is another vector. So clearly a scalar dot product of two vectors, one of which is the dot product of a vector with a tensor. Okay? So I take the ith component of this, the ith component of this, and then multiply and use the repeated index summation convention. This would be mj ej, that's the ith component of this, times the ith component of v, the vector v, so that is vi, right? And I leave it as it is because it's summed over, here it is summed over j, and finally it's summed over both j and I, and this is what I get. So again, I will use the fnjdA is equal to f comma jdv, that very convenient form of the. So this whole term will simply become integral ej I vi comma j dv. So now all the area integrals have been converted to volume integrals. I can by inspection now write the local first law of thermodynamics as is equal to minus that's how we have. This is not a very commonly reported form because of the somewhat problematic, not problematic, there's no clear-cut physical interpretation of that term, which I have to leave it as it is, right? Ej vi comma j. So we won't examine this now because I'm going to write the first law of thermodynamics in a slightly different form, which uses what is called as the mechanical energy balance. So we'll write down what the mechanical energy balance is. The mechanical energy balance looks at dk by dt, that is the time substantial derivative of the kinetic energy. Because if you see in this, we have not made use of the equation of motion F. In that sense, this can be regarded as a slightly purer form of the energy balance. However, we have still used the fact that the mechanics contains two types of forces. We have also used the Cauchy stress theorem. The mechanics is there. We cannot do with energy balance without using some kind of mechanics. But we have not used the equation of motion, and that when it is used, we need to a much simpler and physically probably easier to interpret form of the energy balance. So first let's take that and see what it is. So dk by dt, this is sometimes referred to as a mechanical energy balance. This is kinetic energy only. Is d by dt half rho d square dv. This can be, of course, written as half rho d square by dt dv. So d by dt of d square is d by dt of d dotted with itself. Okay. Now I can use the formula for d by dt of the dot product of two vectors to give two terms. That is dv by dt dotted with b plus b dotted with dv by dt. This is the scalar dot product both terms are the same, and I can write them either as 2 times p dotted with dp by dt or 2 times dp by dt dotted with p. So this is what I have. Now I am going to use the Cauchy's equation of motion, which is rho times right here, rho dv by dE. So I can, what I want is actually rho times this. So this will be rho. So rho times that. So rho times dv by dt is. So now what I will get is 2. So this term is equal to 2 times rho dv by dt is plus rho d dotted with p. So clearly dk by dt, that 2 will cancel with a half there, would be integral is what I have. Now let's look at this closely. So what is this? This is again dot product of 2 vectors. One of them is the divergence of the tensor. We have not done there. This will be EAI comma J. That's the ith component of this. Then combine it with this, and I have this. That's all. Right? EJI comma J is the ith component of the divergence of T, and then I multiply it with the ith component of V. So then by using the repeated summation convention, I complete the dot product. Right? So that's what it is. Now this can be written as integral EJI BI comma J dV. That's not all, minus integral. You will now see that these two terms will actually cancel, because that is what I have there also. And I already have the number to combine the mechanical energy values with what I have there. Right? So minus, there's another term that would be EJI BI comma J dV. Right? So now this can be given, this is important physical significance. If I now look at this, I can also write this as minus EIJ, right? BI comma J dV. So I make use of the symmetry of the stress tensor, right? So this then further can be written as minus EIJ, BI comma J, nothing but the Ji component of the gradient of the velocity vector, right? Ji component. So now I have Eij. The Ij component of one tensor multiplied by the Ji component of another tensor, and by the summation integral summed over both I and J. This will now probably introduce the last of the tensor operations. This is now a scalar product of two tensors. We have seen scalar product of two vectors, a vector product of two vectors, and a tensor product of two vectors. With regard to a tensor, we have probably not seen really a product of two tensors. Now this is a clearly this is a scalar. So I will define this following words for like if I have two tensors A and B, this is defined as a scalar product. If I have two double dots, it's defined as Aij, Bji. So clearly now it's the sum over both I and j. So the net result is a scalar. All the components of the tensors will come in this sum. I'm not going to write it out in all its detail, but this is exactly what I have here. So finally, I can write dj by dt as dji bi comma j dv minus the scalar product of t with the velocity gradient tensor plus now, if you look at this, this is the now clearly, if I want a physical interpretation of this, because sometimes the volume integral is useful to get a local balance, but if I want to get a physical interpretation of this, you can clearly see that this is what I get, right? This is actually t. What I have here is exactly t dotted with v dA, right? So I can, for the moment, replace this as integral t dotted with b dA. So I don't want to go back to the whole procedure backwards to prove this, because I started out with t dotted with b, converted this to n dotted with t, and used the divergence theorem. I got exactly this dAi bi, the whole thing, comma j dv. That's exactly what. I'm sorry, this is written wrongly. dAi, this is dAi. The whole thing, that's what I have. Right? That is what I have. Minus this and plus this. This now can be considered as t dotted with v dA. So you see that the rate of time rate of change of the kinetic energy is simply given by the two of the terms are easy to identify. Those are the two forces, right? And the work done by the two forces on the body, right, leads to an increase in the kinetic energy, right? So t dotted with v dA contributes to an increase in the kinetic energy. Similarly, v dotted with v also contributes. So these are the increase in kinetic energy arising out of the mechanical forces acting on the body. That's the mechanical energy balance. This one, there's a negative sign. Of course, this will immediately turn out to be positive. And this is what we can call as the term arising out of viscous dissipation. Because of the viscous dissipation, it leads to, I have to prove actually that this is greater than 0. Right? It will typically turn out to be greater than 0. Then the curve will become negative. So that will lead to, because of viscous dissipation, it will lead to a decrease in the kinetic energy. That is the term coming out of viscous dissipation. Now, if you combine this with what we have here, right, let's now write the, so what I am going to do is, I have this, now I am going to substitute for this with this. That's nothing but dk by dt. Nothing but dk by dt. Right? So let's write down all those terms again, and you can see how the terms are, some of the terms are going to cancel. What are the terms we will get? So I am now writing a global, an integral energy balance first, which uses the mechanical energy balance. So what will I get? So I get integral dV plus this, which will have plus integral, I write it as t dot v, doesn't matter how you write it. Now I choose to write it the same way on the other side, t dot with v dA plus integral move v dot with v dt minus integral t dot double dot JE. So I have all that. Then I have this right hand side, which may be written as minus integral. Well, I can also leave it as it is here, but I can also write it as integral Ji dI comma JdV. Both are equal as we have seen. So minus, because I also finally want the modified local energy balance, right? So I will better to keep them as volume integrals. So I'll write it like this. On the right hand side I have this, then I have a plus rho B dotted with B. So those are going to cancel out. Plus integral rho. And then I have again plus interestingly these terms cancel each other. And so I get integral rho dE by dE is equal to minus plus the integral, and from which I can infer the local energy value at a slightly different form is equal to this is the form that would be most useful or often widely used in application. Right? So clearly this is an easier form to handle than this. So this form is exactly equivalent to this, what I have written here. It's just in a different form. Right? So rather than dealing with these terms directly and the body force, I now have to deal with there's a heat conduction term and the viscous dissipation term. Effectively, you can see, and I have only the internal energy here, not the half V square. So it's been considerably simplified, but exactly equivalent form to that. Are there any questions? Anyway, if you didn't quite follow the intermediate step, at least the final expression you should keep in mind. So there are three quantities here, right? Which this is the energy balance. As we saw, we developed the equation of motion, and then we said that we need to specify what the stress tensor is. We also need to specify the body force, right, to solve the momentum equation. And then we looked at the linearly viscous fluid, compressible versus incompressible, and so on. So all of that we have already done. And so the stress tensor is very well known to us. What are the models used? We consider only some simple fluid, like a perfect fluid or the linearly viscous, compressible or incompressible fluid. We know how to represent that for those simple cases. So we need to provide models for the heat flux vector, and also for this the specific internal energy. So for that we have to specify the particular fluid we are going to consider, and it will make a difference whether we are going to consider a compressible fluid or an incompressible fluid. Now this is of course independent of that, compressible or incompressible. So Q will take as being given by the Fourier's law of heat conduction. This is again a model. Not all bodies will, just as the linearly viscous fluid responds to only a particular class of fluids. This may be called as a linear heat conductor. It gives a linear relation between the heat flux vector, and this is the temperature. It should not be confused with that stress tensor. Right? So whenever I write the stress tensor, I put a double underscore. to indicate it's a tensor. If you want, I can make this somewhat inverted. But it's clearly the temperature. In the context, it is clear that it is the temperature. This is a linear heat conductor. If you further consider a linear heat conductor with constant thermal conductivity, then clearly it will become the divergence of this, right? K can be taken out minus K. The divergence of the gradient would simply be the Laplacian of the temperature. And so minus of this would simply be given by K times the K is called the thermal conductivity, which we are all very much aware of. That takes care of that. And so let's first consider the simplest fluid and evaluate these quantities, right? And first we will consider the incompressible fluid, linearly viscous incompressible fluid. And this consideration will not only determine how you evaluate this viscous dissipation term, but it will also determine how you handle the dE by dt, as we will see shortly. So first let's take this E is equal to minus Pi plus, this is for the linearly viscous incompressible fluid, because otherwise I will have a delta, I mean the divergence of the velocity will also come in, right? Incompressible linearly viscous. And further we know the incompressible fluid, the density is a constant or the first thing that can be shown before we go to the linearly viscous fluid, it's possible to show that actually D double dotted with this is actually equal to with D for T being symmetric. So that's what we are going to assume all along. It's possible to prove that the scalar product of the stress tensor with the velocity gradient tensor of T symmetric is simply the double dotted product of T with the deformation tensor T. It's possible to prove it, but when we write down assuming that, then T is equal to I take that as let's to be proved, prove it later. Right? So let's now write down one, because this is a common way in which the final expression is written. So what is T dotted at D now? Is equal to minus Pi double dotted at D. Right? Plus 2 that I can easily see, because this is simply the addition of two tensors, and you can see that the double product will also add up like this. Now I double dotted with D, if you want to look at what it is, right? So let's take that I is equal to Aij Bji, so this would be delta Ij Dji, right? So that means I is equal to J term only will count in this, that will simply lead to Dii. And what is Dii? It's a trace of T. What is it for a
0.
It's 0 for an incompressible fluid, because this is nothing but it can be easily shown, we have already shown it, and it is 0 for the incompressible fluid. So this term doesn't contribute, so we get that D this is applied only for an incompressible linearly viscous fluid. So we get this simple form for the viscous dissipation term. Now, if you look at what this we have encountered this is Dij. I. Recall for a second order tensor, which is effectively a 3 by 3 matrix in representation, there are three invariants. One is the trace, of course in this case it is 0. The third one is the determinant. The second one, right, which we would call as phi, right, would be given by half times dii square minus dij. That's how we wrote, but now this can be written as, at our new definition, can be written like this. Right? If you go back to the expression I gave, some of you expressed some doubts about this formula, but anyway, we'll get back to it later. I've checked it many times. This is the trace square minus dij, which I am now simply writing it in terms of the way I have defined this scalar product of two tensors. This is simply the scalar product of D with itself is what that other term is. Right? So if you go back and check these expressions we have given. So now for an incompressible fluid this is 0, dii is 0, which would mean that E dotted and double dotted with itself is actually given by minus 2 times the second invariant of D. So sometimes it's also written as, in terms of that, as minus 4 times the dynamic viscosity times the second invariant of D. So this sort of completes the evaluation of the viscous dissipation term for an incompressible linearly viscous fluid. For a linearly viscous compressible fluid, the formula is going to be much more complicated, as we will see later. Now, what about the last term? If I am able to handle the last term, right, then I would get a simplified equation that is useful for practical application, because the internal energy is obviously dependent on the temperature, because we already have the temperature here. Right? So it will turn out to be a differential equation for the temperature. Right? So to handle that, we need to fall back on classical thermodynamics. If you recall, classical thermodynamics is one of the famous relations which relates the internal energy to the specific entropy and the specific volume. Here, it's typical in classical thermodynamics to take this to be a per mole specific internal energy. This would be the per mole specific entropy. This is the volume per mole. We can easily convert it to a relation. Notation is somewhat misleading because here I have used epsilon to denote the internal energy per unit mass, whereas in typical thermodynamics courses it's commonly we treat per mole. But anyway, now though from an incompressible fluid, whatever this is expressed in terms of per mole or per mass, right? So that is going to be constant. So it's not going to influence the internal energy. Internal energy will not be a function of that. So for an incompressible fluid, I will simply now convert this to a relation simply between the per mass specific internal energy. We have E of S. Because for an incompressible fluid, the density is constant and it is not going to vary at all. So the internal energy is not the no meaning. Because if you draw the associated differential relation, so this is not valid for a incompressible fluid, because as we said, the pressure is not a thermodynamic variable, it is a mechanical variable, so it cannot be defined through the internal energy. So this term simply will not be there. It run out of time. Right? So all I need to consider is this, where I will now define the temperature as simply the derivative of E with respect to S. That part of the relation holds. The other one is really meaningless for an incompressible fluid. We now see how to begin the specific E, because I can express then E in terms of T also, and that will be the specific E, and we will subscribing to the energy equation. You see how that works out in tomorrow's